All right, so today we're going to talk about likelihood-based inference using this package glmm. So first, before we go into talking about the package, I want to introduce generalized linear mixed models a little bit, since I know not everyone, or I'm going to assume not everyone has seen those before. But I am going to assume that everyone has done linear models before, so that's a good place to kind of like start off. So with a linear model, if you're doing inference, then usually the assumptions are your responses are independent, they're normally distributed, and they have equal variance. But of course, we know in the real world this doesn't usually happen, and so we want to think about, okay, what happens if we take some of these assumptions and break them? Okay, so first, if we start off with the assumption of normality, what happens if our responses are not normally distributed? So maybe you have something that's binary, like whether or not a dog returns when you call to them, or maybe you have some count variable like number of apples that you pick or number of dogs in a city block or something like that. So if you have a response that's not normally distributed, then you could, instead of modeling the response itself, you would model, in the binomial case, the log odds of something happening. And if you have like counts, then you would model the log mean. Okay, so that covers if the responses are not normally distributed. How about if your responses are correlated? So this definitely happens a lot in the real world. So maybe you have like multiple measurements on one person, and multiple measurements on one person, and so you're maybe like following a bunch of people through time or something like that. Or you might have measurements on similar people. So maybe you have like cousins or siblings or students in a classroom with a common teacher. So in that case, you would take your linear model and add in an effect for, say, each student, you would add in an effect for each one of these people that you're measuring multiple measurements on, and then you would take some of those parameters and move them into what's called a random effect, and then the other parameters are going to be called fixed effects. So what are random effects? Well, we can think of them as random variables. They usually have a normal distribution with mean 0, but that's not always the case. But today we'll be talking about the normally distributed random variables. Okay, so random effects are unobservable, and we know that parameters are also unobservable, but random effects are not parameters. So what is the parameter in this case? The parameter is going to be the variance of those random effects. So if you have multiple variances, then you would have multiple what's called variance components. All right, so in our linear mixed model, then what are all the parameters? We have those fixed effects, and then we have the variance components, which are, again, the variances of the random effects. All right, so now that we've introduced these random effects, we should talk about what are the assumptions of our linear mixed model. So we have some assumptions on the responses, and we have some assumptions on the random effects. So for the responses, we assume that they're normally distributed, they're independent, and that have equal variance, conditional on the random effects. So once we condition on the random effects, we assume they're independent. All right, and then our random effects, what are our assumptions there? We assume often that they're normally distributed, they have mean 0, and then they have some variance, and the variance doesn't necessarily have to be the same for all of the random effects. All right, so we talked about linear mixed models and generalized linear models. If we combine those two types of models, we get a generalized linear mixed model. So now we can deal with non-normal data, so maybe like binary data, counts, that sort of thing, and data that are correlated. All right, so we're going to, for the G part of the generalized linear mixed model, we're going to be modeling something like the log odds or the log mean, and then we have the mixed effects in there, so that means that we have the random effects and the fixed effects. So the random effects help us take care of the correlation, and then by modeling the log odds or the log mean, that helps us take care of the fact that it's not normally distributed. Okay, so let's see a little example. This is always entertaining to me, an example, but we'll see what you think. So we have this species of salamander that's just a single species of salamander, but they come from two different geographic locations. So you can imagine, like, on one side of the mountain, we have a group of salamanders called the rough butt salamanders, and then the other side of the mountain, we have salamanders called the white-side salamanders. And they're the same species, but they've been separated long enough that maybe they don't really potentially like each other. So we're wondering, do salamanders prefer mating with their own population, or are they just as happy to mate with the other group of salamanders? So that's the research question we're looking at in this example. All right, so the scientists went out, these are scientists from University of Chicago, they went out and collected a bunch of salamanders from these two populations, but they didn't have like an infinite supply of salamanders, so actually they had to reuse some salamanders. So maybe in an experiment on Monday, they put Sally and Fred, the salamanders, in a box and watched to see whether they mated. And then maybe on Friday, they put Sally and Bob in a box to see if they mated. So we're reusing these salamanders, and so we have repeated measurements on the same salamander. So we are going to have correlated data. Okay, so we can imagine that maybe some salamanders are really grumpy, uninterested in mating, while other salamanders might be more interested in mating. So each salamander has their own individualized tendency to mate. And so we want to take that into account with our model. But we can't measure each salamander's tendency because that's just something that's unobservable. We can kind of get an idea by gathering data on Sally, but we can't like actually measure that. All right, and then one more quick thing about these tendencies, we're going to assume that they're independent of each other. So in other words, Sally's tendency to mate does not depend on anyone else's tendency to mate. Okay, so we're talking about the probability of a pair of salamanders mating, so what all affects the probability of these salamanders mating? Well, we have the type of each salamander. So say we have a rough butt female and a rough butt male, then that's one type of cross. And then if we have a rough butt female and a white side male, there's a different type of cross. So we have these 4 different crosses. We could have 2 rough butts, a rough butt female, and a white side male. That's RW. We could have a white side female and a rough butt male, or we could have 2 white sides. So we have 4 different crosses. So that affects the probability that the salamanders mate. And then also we have the individualized tendency of the female salamander and the individualized tendency of the male salamander. So what we're going to do is call the first effect, the first bullet point there, we're going to call that a fixed effect. So that's like the average tendency of this type of cross mating. And then the next 2 bullet points, each salamander's individualized tendency to mate, those are going to be random effects. So those are salamander specific. Each salamander gets their own random effect because each salamander has its own tendency of mating. All right, so now that we kind of understand what's the research question, we can translate that to a statistical sort of model. So our response variable is binary. It's whether or not a pair of salamanders mate. The fixed effects, we have 4 of them, and it's just the log odds of each cross mating. So like beta RW would be the log odds of a rough butt female mating with a white side male. All right, then for the random effects, we said we have 1 random effect per salamander. All of those are independent of each other, normally distributed, and they have mean 0. And then finally, the variance components. So remember, variance components are the variances of those random effects. In the model that's commonly used for this data set, we're going to assume that we have a variance component for the female salamanders and then a different variance component for the male salamanders. All right, so now we hopefully understand what the research question is and what our statistical model would look like. But how would we actually create this model in R? How would we actually do some of this statistical inference? So if you have a statistics background, then you know oftentimes people like to do likelihood-based inference. So first of all, if you don't know what the likelihood is, the likelihood is just a function of the parameters given the observed data. So when we do likelihood-based inference, that includes a whole bunch of things, including maximum likelihood. So in the linear model setting, that's called least squares or ordinary least squares. We can get standard errors, we can get covariances of parameter estimates, we can do confidence intervals to get interval estimation, we can do hypothesis tests like likelihood ratio tests, Wald tests, that sort of thing. Those are all sorts of likelihood-based inference. And then also the likelihood is used for like AIC, BIC, and other sorts of things. All right, so hopefully we can see likelihood-based inference includes a whole lot of stuff that probably you've talked about before. But in case you are still doubting likelihood-based inference, one more reason that we would want to do some likelihood-based inference for generalized linear mixed models is that the maximum likelihood estimator is going to be asymptotically normal. And then when we want to find the covariance matrix of the parameter estimates, that's going to be really easy. We just need to take the second derivative of the likelihood function. Okay, so now we can see likelihood-based inference, I argue, is a good idea. But now we have to talk about, well, why is this hard? Because if this wasn't hard, then probably someone a while ago, older than me, would have done this. So to think about why likelihood-based inference is hard, we need to think back, what is our definition of likelihood? It's a function of the parameters based on the observed data. So our observed data does not include the random effects. Random effects are not observed. But random effects do affect whether or not the salamanders mate. So we can see that we have a problem because we cannot have our likelihood based on the random effects, but the random effects do affect the response. So what that means is that we have to integrate over those random effects. So in the end, our likelihood is actually this integral, and it's usually a pretty high-dimensional integral unless you're working on a pretty trivial problem. Okay, so what are you supposed to do then if the likelihood-based inference is the way to go, but likelihood-based inference is hard? So if you have a simple problem, like one random effect per observation, then you could do numerical integration. And then, so the problem with that you can probably notice is that you can only have one random effect per observation. Another option might be using Monte Carlo EM. So we know that EM is for maximization. So then we could maximize the likelihood using that Monte Carlo EM. The problem with this one is that, yes, it definitely would give you the Monte Carlo maximum likelihood estimate, but you would have to do a whole separate calculation to do to get the variance matrix, and so that's maybe not the way to go. And then a popular option that people usually do or have been doing is use the package LME4. So that doesn't do likelihood-based inference for all problems. It does likelihood-based inference for more simple problems like the one random effect per observation. So it instead takes the likelihood and just pretty much does a bunch of approximations to end up with something called the penalized quasi-likelihood. So the problem with that is that your estimates are not going to be maximum likelihood estimates, and you don't know how far the penalized quasi-likelihood estimates are from the maximum likelihood estimates. All right, so then what I did is I created this R package, glmm, released it in 2015. It was part of my PhD work at the University of Minnesota with my advisors, Galen Jones and Charlie Geyer. So since we don't have a ton of time, then I didn't put the R code in it, but the R code is all on my website and you can check it out. So the slides are on my website, and then there's also a vignette on my website. So the basic idea is that my package approximates the entire likelihood function using Monte Carlo and importance sampling. If you don't know what importance sampling is, don't worry about that. And a good thing about it is that the estimates that it produces converge to the MLEs as you increase your computing time. And other things also converge, so like the likelihood approximation converges and all the inference also converges. So just quick talking back to the salamander results, it ends up, yes, the probability of salamanders mating does depend on the crosses, but we don't have enough time to probably talk more about that. But I figured I should probably tell you that since I talked about the salamanders before. Okay, and then how do the point estimates compare? So here on the first row I have the results created by my package. Second row has the results created by Monte Carlo EM. And so we can see when we look across those different point estimates, they are pretty close to matching up. And then when we look at the point estimates created by LME4, which is, again is penalized quasi-likelihood, we can see that the point estimates for the fixed effects pretty much match up, but then the variance components are too small. So again, remember, MCEM converges to the actual maximum likelihood estimate. So by having my estimates look pretty much like the MCEM estimates. That's good. That means that we're agreeing on what the maximum likelihood estimates are. And then LME4 is getting point estimates that are a little bit too small, which is consistent with research on penalized quasi-likelihood. Okay, and then so that you have a general idea of what my package does, it will create your maximum likelihood estimates using that Monte Carlo. It'll reduce point estimates, standard errors. It'll give you the likelihoods. You can do things like likelihood ratio tests. It'll give you the gradient and the Hessian and a whole bunch of other output that I didn't include here. And then as a follow-up, you can do things like get the variance covariance matrix. You can get the standard errors. You can get the Monte Carlo standard errors. You can use the confident function to do confidence intervals. All right, so I know that was a whirlwind of information, but all of these slides and my vignette are all on my website, cknudsen.com, and I invite you to definitely email me, knudsen.ust@gmail.com, if you have any questions. So, thanks.
You did not mention R-Stein out, which is the latest in town. What's the difference? Why does it's quite overlapping, I think.
I actually haven't checked out that one, so.
Because that uses STEM, and the same interface as useR as LME4, and is very well developed.
All right, I will check that out.
Before, but I don't use it.
Okay. I will check it out.